Hi everyone. I'm here to talk about my semester-long project to build a LiDAR sensor. Using a Raspberry Pi with OpenCV and Python, along with several other components, the goal of this project was to build my own field deployable LiDAR sensor and map a small landmark on campus. After careful consideration, I chose an inspirational and geometrically interesting target, the statue of Frederick Douglass outside of Hornbake Library. The height and shadowed areas posed a bit of a challenge, but it turned out to be a great target. It has easy 360-degree viewing access. It gets very dark at night, which is when it's easiest to scan. And the cubic base served to be a great geometric reference to help process the LiDAR data. Now, the sensor had very modest origins and was gradually pieced together throughout the semester. I started out with a thin piece of fireboard to set the components on and went from there. It's not very compact, but everything is easily accessible for when a component needs to be fixed. Now, I got all of my hardware problems out of the way early on, buying a faulty battery and a camera case that actually strained and broke two of my cameras. However, after these problems were resolved, I made sure to mount everything securely on the sensor. It isn't the prettiest, but it turned out to be very reliable. Here is the LiDAR sensor. Starting over on the left, we have the transmitter or laser pointer. The button is held down with a piece of Velcro, while it is kept securely in place by these two yellow 3D printed mounts. This makes it easily removable for when batteries need to be replaced. Moving on, we have the Arduino with the IMU chip. This is responsible for producing three XYZ coordinates that determine the sensor's angle location or orientation. Right here we have the mounting hole for a tripod with a nut to secure it. This big white block is the external power source. It's attached with Velcro, so it is easily removable to be recharged. Lastly, we have the receiver or Raspberry Pi with a camera, which gives a pixel location of the laser spot, ultimately determining range. And finally, we have this Ethernet cord right here, which connects the device to a computer so it can be controlled. After finishing the final configuration of the sensor, it was calibrated by taking incremental measurements and processing them in Excel and MATLAB to account for the axial differences between the laser and camera. The next step was to go ahead and try the sensor out on my target. For the first time, I went ahead without a tripod, and to avoid any noise from other light sources, I waited till well after sunset every time I scanned, which should be evident from how dark this video is. On my computer, you can see the laser being tracked, with the angle orientation and pixel location being logged. On the first scan, I made sure to include the steps and pedestal in because they're easily recognizable shapes, and I actually thought the points ended up coming out pretty well. Next time I went out, I was definitely more prepared with the tripod, a pack of batteries for the laser, and a full charge on my laptop. It was helpful to bring a tape measure to gauge the actual distance I was taking scans from. It would help later when it came time to process the data and make up for some of the human error involved in the scanning. For example, it wasn't always easy to tell whether the laser was exactly perpendicular to the face of the statue. Although the tripod took care of movement in the Z direction, it didn't stop me from moving closer or further away from the statue each time I shifted over to take the next scan. I tried to take scans that would capture all the key features, so they weren't always evenly spaced. Although it was somewhat annoying staying within 6 feet of my laptop as I moved along the X direction, using an Ethernet cord seemed to be the right decision. I never suffered from connection problems between the Pi and the laptop. Now, between the front and back face of the statue, I took about 20 scans. The instrument performed well throughout the whole process, and it even survived a fall. Using a graph of the X angle of the sensor, I parsed up the data into each respective line scan and applied range offsets in the Y direction to account for movement on my part while I was scanning. This is where scanning the base became extremely helpful. I was able to clearly see which lines needed adjustment by making sure the base was aligned in each scan. After filtering out the bad points and making those adjustments, I was able to turn my data into a 3D point cloud that resembled some prominent features on the statue. The last step was to put the front and back scans together in MeshLab. As points, they lined up pretty well. However, my MeshLab skills could definitely use some improvement, whether it was due to not having enough points or lack of training in MeshLab. The final mesh didn't come out as intended. Regardless, it's been a fun semester, and I hope to get into much more advanced LiDAR systems as I progress throughout my career.